So this is over Q, but well, if we instead the Q we have as usual K and S. Then instead of Runge condition, we use RS. Runge S condition is that the action of the absolute Galois group now of the field K on the poles has at least or strictly bigger than S orbits. And the argument is absolutely the same then. It goes for every, so if we have S integral point, then for every V in S, we find some of the orbits where it will close, and then still one orbit will be left to use here as sigma 2, to use for the poles of Z. And then same argument, I don't want to repeat, but well, same argument and gives the same result. What is remarkable here, so notice that the condition R or RS, contrary to the assumption of Siegel or effective Siegel that I stated or whatever, the condition is not geometric. It depends, of course, on the field, and the result also depends on the field. So we can never, with Runge's method, we would never obtain Siegel's theorem in the absolute sense that I stated on the last lecture. It depends on the field, the condition. And of course, when field is big enough, we do not get as many orbits. So if field is big enough, it's simply all poles are defined over this field, and sorry, not all poles. No, we have too many elements in the set S, and if we have say more than the number of the elements of the set S is at least as big as the number of poles, then we can never obtain anything. So, so the condition is not geometric. But what is interesting, that the result is geometric. The bound is uniform in K and S. The bound does not depend on K, does not depend on S. It depends only on the geometric data, the curve and the coordinate. Then for X in for P in X, we have the height, well, say with respect to X to P or whatever the height is bounded by some guy depending only on the curve and the coordinate, effectively depending, but not on the field, not on the set S. So it is totally uniform. And so, say for instance, Bombieri suggested to speak on little s integral points. So points which have in the denominator at most little s, where little s is not a set, it's just a number. At most little s places in the denominator where little s is smaller than the number of orbits. And then whatever little s is, we have this bound. And so here the condition is not geometric, but the result is uniform, is geometric. And usually it's quite good. In any case, it's always much better than what Baker's method can give. Second remark. Let us look at the last part of the proof. So we see that the proof gives what? Either x of p is smaller than some constant c1, or z of p is 0, and which means that x of p is smaller than some constant c2, right? So in practical situations, usually it is C2 which dominates. Here, if we speak on this constant, C2 is bigger than C1, this one. And so it is C2 which dominates. But assume we are what I call lucky case. The lucky case is the following, that not that only that zeros of z contain the z sigma 1, but they are just coincide with this z sigma 1. Lucky case is zeros of z is sigma 1. So has no zeros outside the poles of x. So z is sort of a x unit. So exactly the object that we like to have in Baker's method. It's not always possible to achieve. For instance, in the baby example, this was not the case. But sometimes it is. And in a while we will see that for modular curves it is exactly the case. It would be when Runge's method applies to modular curves, it would exactly be the case. And in this case, there is no C2 because simply it cannot be 0. All zeros are poles of x. So z of p simply cannot be 0. It's distant from 0, and we have, it is only the constant C1, the first constant, which works. And it gives numerically much better result in this lucky case. But of course, it is not always achievable. So this kind, whenever Runge's condition is satisfied, this is something we can always have. This is only if we are lucky. Good. Okay, so enough for general Runge's method. And now I will speak how it applies just on one example. I will show how it applies so there are many applications. Actually, initially in this course, I plan to speak on plenty of applications, but well, you see, you always plan more than you can do. Well, for instance, basically, all this famous Charey-Sarada and so on, it is sort of Runge's method. But now, you see, I just simply cannot go into this. This product of consecutive terms of arithmetical progression with prime difference cannot be a perfect power or so. This is quite non-trivial application of Runge's method. And it was Aaron Levin who realized. Actually, let me give this reference. If you want to understand how Runge method works, and see many examples and really just to get an idea, but only in qualitative sense. No, I think almost no quantitative results are there, but qualitatively it's very good. Just look at the article by Aaron Levin, Variations on the theme of Runge. Something like in our journal, Journal de théorie des nombres de Bordeaux, some 2007 or so, you will find easily. Just Levin has only one article called like this. It's wonderful, absolutely wonderful article. I think he published 2 or 3 articles in our journal. This is one of them. Absolutely wonderful article. I strongly recommend to anybody who wants to learn about Runge's method. So his notation is a bit heavy, but you see, you very quickly, but it's also very logical. So you very quickly get used to his note, and it's repetitive. So once you understand what his notation means, then it's easy to follow. And you just read this article as a poem. You see, it is really wonderful article. So strongly advise to look into it if you want to see what Runge method means. Sorry? Journal de théorie des nombres de Bordeaux, yes. Now, applications of Runge method to modular curves. I will just consider one problem because it is close to my own work, actually completely related to my own work, and I will see how Runge method, well, it's the result which is obtained uses beyond Runge method many other tools, but for me, Runge's method contribution is quite non-trivial and even maybe crucial in this case, so I think it would be a good illustration. So now it's called Serre's uniformity problem. So there are many problems of Serre, and some of them can be called uniformity problems. But I will speak on one problem. Initially, I will speak about elliptic curve, but then we will switch to modular curves. So let E be an elliptic curve. Let's assume it over Q. The result of Serre that I will state, it also works over arbitrary number field, but further work only goes for Q over Q, so I will assume from the very beginning that the curve is over Q. And let also P be a prime number. Then we associate to this elliptic curve and to the prime number P, we associate what is called the Galois representation attached to the couple EP. And well, it's again tradition to denote it by the letter rho. So again, this rho has nothing to do with the distance that we use. So it is rho E P of the absolute Galois group of Q to, well, what we have? We have the absolute Galois group acts on the P torsion just by conjugation. And this action, of course, respects the group law. And so this means that if we write an P torsion as is isomorphic to Fp squared as a vector, as a two-dimensional vector space over Fp. So if we fix a basis, we have this isomorphism, and this means that we have a representation of Galois is GL 2 of Fp. And the question, what one can say about this representation? For instance, it is known that it's almost always irreducible, but we want to speak of not irreducibility. We want to speak more. We want to speak whether, on the question whether it is just surjective, just the image is everything. So, and Sorry?
You want to be away from the label? P primes dividing the level of the curve?
Level of what? It's just elliptic curve, no level so far. So far, no level, just elliptic curve. So far, no, just elliptic curve, good. And now question, is GL2, is the, sorry, image of rho E P, well, let's put a more vague question. How big is the image? How big is the image? Why, and why we expect this image to be everything? This is simply, well, follows from general philosophy of Galois theory. We know that Galois group is an object that has a sort of structures like a gas. It occupies, unless some constraints are put, it occupies all available space. So if we just, for instance, if we take just a random polynomial over Q of degree n, then unless we do, well, if it is indeed random, then with the probability 1 in very high extent, the Galois group will be everything, symmetric group of order n. And here, the image of this representation, it is just the Galois group of the field generated by all torsion points. Generated by all torsion points. And so, again, of course, there are some constraints. So it cannot be symmetric group of order, say, p squared. Because the Galois action should respect the group law. But otherwise, we do not see any constraints, and so we expect this. We expect this to be the full biggest possible guy. So it is GL2 of FP. Well, there is one constraint in a special case when E is a complex multiplication curve. So if E is Cm, then the image cannot be GL2. Because it must be contained, well, depending on how P behaves in the CM field, it must be either contained in normalizer of split Cartan or non-split Cartan or in the Borel subgroup. So in one of the three subgroups that I spoke in the last lecture. Because CM means that we have some additional, also the Galois action should in certain sense respect the complex multiplication. And so we cannot have everything. But so it is natural here to assume that image is not CM. That our curve is not CM. And in this case, Serre, in his very famous article of year 72, Propriétés galoisiennes des points d'ordre fini sur les courbes elliptiques, something like this. Yes, Galois properties of finite order points on elliptic curves. And well, I remember when I spoke on this in Montreal, Henri Darmon told me, and you know that this work was done when Serre was visiting McGill. So it's really so famous result that people in very glorious West University of Canada are proud of the fact that this work was done there. So it's really very important work. Serre proved that it is indeed the case provided P is sufficiently large. If P exceeds some guy depending on the curve E, then, and E not CM, then image is GL2. And now, what one can say about this guy? There are some estimates due to various people like, I think, Masser, Pillarin, Cojocaru. So certain people obtain certain upper estimates for this P0. But actually, Serre himself suggested that most probably P0 must not depend on E. And this is what is called Serre's uniformity. Well, I would say Serre's uniformity conjecture, but I remember that he objects of calling this conjecture. He calls it a question. So let's call it Serre's uniformity problem. Difference. Conjecture asserts. It's like Lemmer's problem. So is it? We can call it Lemmer's conjecture. We can call it Lemmer's problem. You see. Yes. So Serre's uniformity problem. Is it true that there exists some number P0, absolute constant, such that for any E not CM and any P bigger than P0, we have the image is GL2. And there is even a more optimistic, well, this time let's call it conjecture, that it is very possible that P0 is just equal to the remarkable number 37. At least there are examples on the level 37 when it is not true, and there are no examples above, and there are also some theoretical indications that it is very possible that this number is 37.
You mean there exists an elliptic curve for which
Yes, for 37, yes, there exists an elliptic curve for which it is, it's not CM, but the image is contained in the Borel subgroup. I don't think that I can reproduce it, but it is in Mazur's work. Now let us restate this problem on the modular language. So now assume that is not surjective. The image is not full. Then the image must be contained in a maximal subgroup of GL2. And moreover, well, there are some wrong maximal subgroups. It is known that the image must contain matrices of any determinant. This follows from the existence of the Weil pairing. So this means that image must be a maximal subgroup of full determinant. And these subgroups are well known. There is full classification of them. So the determinant of is surjective on let's say on P star. So the determinant is on here, And this means that it must be maximal subgroup of full determinant, and there are all of four types of these maximal subgroups. With determinant equal to everything. First, Borel. So I already spoke on these subgroups last lecture, so I will now be brief. So which is conjugate to triangle. Normalizer of split Cartan. So split Cartan is conjugate to diagonal matrices, and if we normalizer, as we say, split Cartan, as we said last time, split Cartan is a subgroup of index 2 in its normalizer, and to obtain normalizer, we just take also anti-diagonal matrices. So this and these matrices we take, and we obtain normalizer of split Cartan, or any subgroup conjugate to this guy. So in geometrically means either all contractions along two vectors, or also we can interchange between these vectors. Normalizer of non-split Cartan. So here, as we said, it is just analogs of, in the real case, it's just symmetries and rotations. So rotations, non-split Cartan, symmetries, obtain the normalizer, and of course, well, homotetities. So. And there are also exceptional subgroups, small subgroups. And these are small subgroups. They are isomorphic to one of the groups A4, S4, and A5. Alternative of order 4, symmetric of order 4, and alternative of order 5. And what we have to prove that that for sufficiently large P, the image cannot be contained in any of them. Now, Serre disposed already in his article, he more or less explained that this is not possible. Same article. Now, what is Borel? Assume that the image is contained in Borel. This means that simply that this elliptic curve has a rational P isogeny. And then Mazur showed that exactly for P greater than 37, there can be no rational P isogenies if the curve is not CM. And for P greater than 163, no P isogenies, no rational P isogenies at all, even for SIM curves. Mazur. For P greater than 37. Now, the case of normalizer of split Cartan was completed very recently in a joint work with Pierre Parent and Marussa Rebolledo. So there were two articles, one due to Parent and me in Annals of Mathematics, the other joined with Rebolledo in Annales Institut Fourier. And so initially we proved that with Parent that P must be bigger to some unspecified constant, but well, the calculation gave something to 10 to 80 or so, which is bigger than the number of all particles in the universe, which is a bit huge number. And then with Rebolledo, we managed to reduce it to what we have. So here is for P greater, strictly bigger than 13. And also, well, I think it was known also it is true for P equal to 11. We also believe that this is true for P equal to 13. but our method failed. I will maybe say one or two words why at the end if I have time. But it's already, since 13 is smaller than 37, then it's more than enough. So conjecturally, we can write p greater or equal 11 here. Now, what is left? Just to complete. So this was year 2011 and 2013, 2 articles. Now, to complete, one should deal with the non-split case, the normalizer of non-split Cartan. And in this case, all methods remarkably fail. Everything just breaks down, so nothing works. In particular, the Runge part of our argument fails completely here, because simply Runge condition is not satisfied. And this is a probably quite difficult open problem. There are some deep reasons why it fails. I'm not going to speak on them, but probably we need some drastic new ideas to treat this case. Good. Now I will say a few words how this theorem was proved. Good. So let us first rephrase this argument in modular language.
The last case, the SAR case,
The non,
all primes?
sorry,
What's the last?
exceptional.
No, I'm saying for all primes, is this true?
Well, maybe for very small primes. Maybe this is not true for primes. Well, I think starting from p equal to 7 or so, it must be true. So I think that yes.
So this 37 actually comes from the second case.
37 comes from from this case. Yes. In our case, it is 13, and we believe that it must be even just 7. But because for 11 it is also true. But the fact that it's true for 11 was known since ages. What it means that the image is contained in one of the subgroup. It means that this elliptic curve gives rise of a rational point on a certain corresponding modular curve. So, for instance, the image rho e p is contained in Borel. Implies that E gives rise to an integral point, rational point on x0 of P. Because it's exactly who classifies elliptic curves with P isogenies. Similarly, split Cartan, split Cartan implies that we obtain a rational point in X SP plus at P. And non-split Cartan implies that we have a rational point in. So the result is just to describe the set of rational points, so to show that the only possible rational points here are CM points, the points coming from CM curves. So want to show that X, 0 of P Q or X SP plus of P of Q or X and SP plus of Q. Any of this is contained in what? Cusps. Well, cusps can be rational points, of course. At least here and here there are rational cusps. And CM points. CM points are points that come from CM elliptic curves. And so what we obtain? We obtain a problem of finding rational points on modular curves. It's a Diophantine problem. Fortunately, one speaks here about rational points. But it turns out that actually, at least in the first two cases, we speak about integral points. Because, well, Mazur, part of his argument here, he proved that actually all rational points except cusps are integral. By the way, we know that CM points are always integral. J invariant of a CM curve is always an integer. But CM points are not too many because CM points are with rational J invariance. We know not too many fields with rational J invariance, so not too many of them. Yes. Now here, so yes, if P is OXSP plus of P of Q and not cusp, then J of P is actually an integer. So we speak on integral points. So in this case, it was proved by Mazur as a part of his argument. In this case, it was proved by various people, by Mazur, by Momose, and by Merel. It was not a joint work. Simply, they considered different cases. Mazur proved it in almost all cases, but some cases escaped his argument. Momose completed, but there was still one nasty case of P equal to 2 and something was wrong, I believe, for 2. And Merel completed this missing case. And in our article with Pierre, you can find a one-page proof or uniform proof that treats all the cases simultaneously. But it's a serious argument. It uses all kinds of, so it is based on some very, very deep stuff, like the work of Kolivagin, Logachev about analogs of Bershov-Newton-Dyer or abelian varieties. So it is a very deep result. It's deep, but it's done. And here already the first thing that remarkably fails for this, there is no way of proving by the same method. Same method fails for this curve. So we cannot be sure that the points, rational points, are integral here. And it is even possible that they are not. Good. Now, good, we have integral points. Say, well, since for x0 of P it was done already by Mazur, so let's concentrate on this curve, the one. So we have x SP plus of JZ. And we already proved, at least Baker's method gives a certain bound. Well, unfortunately, the bound is not nice, but fortunately, in fact, Runge's method applies here. Because what is the set of cusps? So far I said that there are P plus 1 over 2 cusps, but in fact, the cusps, there are 2 orbits. There is 1 cusp over Q, and P minus 1 over 2 cusps defined over the real cyclotomic field. And they are conjugate. That's exactly the degree of this field. They are conjugate. So we have 2 orbits. So Runge works. Great. And since everything is very, very explicit, because now we have two orbits, we can make, now using Ziegler function, we can construct this Runge function is very explicitly. And moreover, it will be a modular unit. It will be supported only on the cusp. So we're in the lucky case. So this is a cusp at infinity. So call it P, also call it P0 and call this P1, etc. Sorry, let's call it better C0. It's this C1, etc. C P minus 1 over 2. Then we can find the function z there exists a function z which is over Q such that the principal divisor of z is what? Is P minus 1 over 2, this P0 minus P1 plus etc. C. C1 plus etc. plus C P minus 1 over 2 times some number m. And well, I don't remember the exact value for this m, but it was something like P minus 1 squared or whatever. So not very horrible. And z can be constructed very explicitly using Ziegler functions. That I spoke in the beginning today. And this z serves as Runge function, either z or z minus 1. So if we are close to one of, if our integral point is close to one of these cusps, then z minus 1. If our integral point is close to this, then z is Runge function. So one of them is Runge function. And it is a lucky case, because zeros and poles lucky case, as I said before. Zeros, so z does not vanish outside cusps. And when everything is so explicit, we can do the things very well, and we obtain the bound. We obtain the bound that so Runge's argument gives the following: that if P is x sp plus of P of Jz, then the height will be log x of P, in this case, log J, sorry, of P, is bounded by some constant square root of P. Actually, even with the constant, I think it was something like 2 pi or whatever. So something very, very, very explicit. Well, still we have this small, how to deal with small points. And then comes one more idea, how to dispose of the small points. And here we have to use one more quite non-trivial thing, is isogeny bounds. By the way, notice that here it works perfectly well also when the point is CM. So far we did not use the fact that the point is not CM. But it is used in the next part of the proof. So there is a famous series of works which was initiated by Masser and Buchholz, and mainly done by them, but also by other people, about bounds of isogenies, bounds for isogenies on of abelian varieties. If we have two isogenous abelian varieties, then what is the smallest isogeny between them? What is the smallest degree of isogeny? And one can bound this in terms of what is called the height of abelian varieties or whatever. And it was instrumental for them to obtain some important things like analytic subgroup theorem or whatever at all. But well, in our case, we're only interested with the elliptic curves. Now notice what's important. So far I did not say, I promised to give you the modular interpretation of this curve, but so far I did not do it. So do I have 10 more minutes? Then I will finish completely everything, good? So what is, so first of all, xp of p. Sp of p is, so we remember, x0 of p classifies cuples, curve, p isogeny, right? Here, this guy classifies triples, where A, B, independent p isogenies. So not the same. So different kernels. Now what is X plus? X plus is, we take a bigger subgroup, and so XP has XP of P. So this corresponds to a subgroup of twice as bigger. So we have a natural covering of degree 2. Which means that simply we have here some involution. What this involution means, what we do, what is involution? We just exchange A and B. And so this means that this guy, it is just this involution is just E AB to E BA. And the quotient by this involution will be this. And so what is this? This means that XSP plus of P is just cuples E AB, where AB is unordered pair of P isogenies. So AB and BA are the same. It classifies objects like this. Here is the modular interpretation of this curve. So anyway, what we have? We obtain that if we have here a rational point, we don't even care whether it is integral or not. If we have a rational point on this curve, then it gives rise to couple E, A, B, where E is elliptic curve over Q, and A, B, so unordered pair of P isogenies, and as a pair it's defined over Q, which means that either both isogenies are defined over Q, but this is not possible by Mazur work, so we know already, or they're defined over some quadratic field. So we obtain that A, B defined over k, or k of degree at most. And now what we have this picture, we have E, we have to some other curve, A prime, A, and to some other curve, E second, we have B, right? But H isogeny has its dual. So we have from E second a dual isogeny to E. And what we obtain? We obtain from E second to E prime an isogeny of order P squared. Well, E second is of course not our curve E, but it is known by Faltings that the heights of these two curves are the same, almost the same, so do not really vary much. Now, what was the isogeny bounds? Well, I said Masser-Wüstholz, but actually we used the result of Pellarin, who refined the work of Masser-Wüstholz. It was exactly what we need. Isogeny bound of Pellarin. And this bound says that if E prime, if E prime are isogynous, and at some point, one has to assume well, in Pellarin's bound it was not important, but at some point here, one has to assume that yes. So the point was that the minimal isogeny. Yes. The point is the following: that if the curve are not CM, then cyclic isogeny is minimal. So if we have, say here, cyclic isogeny of degree P square and there is no CM, then this is minimal isogeny. But well, isogynous, then there is isogeny from E to E prime of degree bounded by some constant, depending only on the degree of the field, isogynous over everything over some field K, some constant depending only on the degree of the field, and very tamely depending, where D is the degree of the field K, times the height of the J invariant of the curve E squared. And what was important for us that it was square, because say Masser-Wüstholz had 4, and 4 was not sufficient. Square was, anything smaller than 4 was sufficient, and he had square. There was also another bound by Viada with 3, which was also sufficient. Good. So we have here this. And now let us look what it gives. So this isogeny E second E prime P square cyclic of order P square. And since E prime non-CM, it is minimal. Which means that P squared is bounded by this guy. And D is here too. So we have C of 2, some absolute constant, times height of, and what is GA? Is J of P. And what is height of J of P? It is log J of P. So well, height of G, actually GA second squared. But height of GA second is almost the same as height of GE by Faltings. Faltings said that isogynous abelian varieties have almost same height. So it is bounded by C height of GE square, which is C log J of P squared. And then we see that P is bounded by some constant log J of P, which is bounded in turn by some other constant square root of P, and then P bounded. So the argument we see has three main ingredients. Integrality, Maisor-Momo-Zemirel. Our Runge part is this, and the isogeny part is the work of Masser, Wilsholz-Pillarin.
It's very explicit, right? This is bound is you got some.
Yes, it is explicit. This constant is small. The problem is with this constant. This constant is huge. In Pillarin's work, it is 10 to some huge power. So this constant is huge in Pillarin's work, and therefore, in our first article, we obtained a huge constant here. Really, really enormous. Then came a numerically much sharper bound due to Gaudron and Raymond. And they were, in fact, motivated by our work, just we wanted to reduce it. Now, numerically refined Pillarin. And this gives us something like P bounded by C to some power 8 or so. And below, for small p's, there were some previous work of Paran and Rebolledo that allowed to treat every particular p, allowed to show for every particular p to very quickly verify that for this p, the statement is true. So it was just done on a computer. And it was unfeasible with the previous bound when it was, say, 80 or so. But with this, it was totally feasible. Some previous work of Paran and Rebolledo implied that small p can be also treated. So this is, and then we just went down to 17. 13 did not work because integrality part did not work in this case. So we don't know anything. Now, in the non-split case, as I said, the only thing we know is bound due to my two PhD student, Bajolet and Shah, for integral points. But we don't know whether integral points, whether all rational points are integral. So, and there was very recently appeared another bound due to von Kannel, which probably is sharper than the one due to my students. So I still have to check.
Generic elliptic curve, where does the image lie inside among those four?
Sorry?
There are four possibilities. Is there some way of guessing that which is a generic case?
Well, the generic case lies in neither.
So if you take a random elliptic curve,
A random elliptic curve, it is full. Like for random polynomial, the Galois group is full. So for a random elliptic curve, it's very good. It's full. So random elliptic curve is good. So here we just have to show that there are not many non-random guys. Yes. So I think that it is all. So I don't need tomorrow's hour. I think that I'm done. Yes, and you will still catch your bus, right? Yes, good. Okay, so thank you for attention. It was a really great pleasure. Thank you for everybody, for first of all for you to organizing all this, and for all the listeners for being for listening and asking questions, and so simply being here. And well, I hope it's not the last time.